Welcome to the third lesson of Nerd Academy. We are a bit late today. Today we will be discussing basic GLSL and the Mandelbrot set in Shadertoy. I will be sharing my screen here. Actually, hold on. I need to set it to the...
What do I need to open for this? VS Code or what?
we will not be using VS Code. We will be using Shadertoy. So, yeah. So, this is Shadertoy here. Uses GLSL code, if you can see this. It's similar in structure to C, like the C language type, where each expression ends with a semicolon to kind of end them, unlike Python, which is just new lines. You got your data type definition, the variable name, blah, 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 blah. Now, I should first ask, how familiar are you with this kind of format for code? Do you have any background at all?
Yeah, much. Coding's P5JS, all, schools covered it, I've covered it, I'm good.
Okay. Now, are you familiar with the Mandelbrot set at all?
No, is it the thing that makes, those fractals?
Yeah, it's a fractal. A very specific kind. It's this thing.
Yes, it's a fractal.
Yeah, and it's generated on the complex plane. Are you familiar with complex numbers?
No, I've heard of them though.
Okay, so I'm going to go over complex numbers and how this is even brought into existence, but I'll do that after I tell you about the basics of GLSL, of how to actually render something on the screen, and then I'll get into the complex numbers and how to actually render the Mandelbrot set. So, do you have this Shadertoy window open? Just shadertoy.com/new.
Yes. Does this work? I enable push to talk. Yeah.
Okay. So this shader code, what it does is it takes in the frag chord. Now, a fragment is basically just a pixel. So it takes in the location of the pixel on the screen here, and it outputs the color. Now, the frag chord, the location of the pixel, is a 2-point vector. You know what a vector is, right?
Yeah.
Okay. So yeah, you got your x coordinate and you got your y coordinate. I believe the lower left corner is the origin, and then it counts up, like you'd expect. Now, frag color is a 4-point vector. It's the red, green, blue, and alpha channels. And the alpha channel isn't really used in Shadertoy. We just set that to 1. Now, this is the default placeholder thing on Shadertoy. So it runs the main image function, and it sets UV to whatever the coordinate is divided by the resolution. And it divides the x component of the coordinate by the x component of resolution, and then the y component of the coordinate by the y component of the resolution. And so that's how you can divide one vector by another vector, is you're just dividing each element by the respective element in the other vector. Does that make sense?
Yeah, so, yeah, pretty much.
Okay. Yeah, and so when it defines UV, it's basically just turning it from 0 to 800 to 0 to 1, and it becomes a float. And then this thing here, color, it's a vector 3, so it's RGB. It takes the cosine of time plus uv.xyx, so it's creating a 3-point vector where the first component is the x of the UV, and then the y of the UV, and then the last was the x of the UV, and that's just kind of an arbitrary pattern, and it adds this constant vector to it, and it adds time to each of those parameters, Then it takes the cosine of all of them, multiplies it by 0.5, and adds 0.5 to each parameter. Basically, when you add a single constant to a vector, it applies to all three of them in this language. And so it's really nice for that. And this sort of thing it creates this blur pattern that you see here. It's just a funny pattern that is just there.
Why 0 to 4?
0 to 4 is completely arbitrary. So if I were to change it to 0 to 2 and then run the compile button, the color is different. Or if I were to change this to, say, 1,000 and then compile that, it looks a little bit different. And you can see that's a lot brighter, especially on like the blue channel. Or if I were to set 0 to, say, -15 and then compile that, it's going to look different. So the numbers that are picked are completely arbitrary. Now, if you remove all of this and then set that to 0, 0, 0, 1, and then hit compile, it's just a blank black screen. And so, you set frag color, which is already defined as a vec4 here, to vec4 0, 0, 0, 1. And so that's what you get. If I set it to 1, 0, 0, 1, you get red and yellow and whatnot. And so we have absolute control over what it looks like through this. And we can do any sort of crazy math we want to. And yeah, does that make sense so far?
Yeah, so you're basically getting the stuff on the screen and altering it.
Yeah. Yeah, and this function is applied to every single pixel on the screen. That's what a fragment shader does. And so let's suppose the first thing we want to draw is a circle. Just like before, I'm using Control Z to get the stuff back. We can use this UV thing here, just like before. But instead of using this for the color, we can bring in the Pythagorean theorem to essentially get the distance from the origin. And so we can do vec3, and inside of that, if you have a vector and then one parameter inside, it will apply that parameter to all the entries. So if you have vec4, 0, it'll just have 4 zeros. Does that make sense?
Yeah.
Yeah. So for this, if we want it to be a grayscale, we only have to assign one entry. And so for this, what we can do is we take the square root of uv.x times uv.x plus uv.y times uv.y. And this will plot out the distance like that. So that's clearly the origin. And then that's a distance of 1, that's a distance of 1. Obviously 1 is the limit, so you can't really see it beyond that point. But if you multiply it by 0.5, you can see the full gradient up to around that point. Or actually more like 717, I believe it is. Yeah, there. Now we have actual white there. So yeah, and this is plotting out the distance from that point. And then if we were to modify the UV so that we want this to be in the center, we could modify UV minus, let's see, how about vec2 0.5, and hit the compile button. Yep, there it is right in the middle. And you get what this command here does, right? Can you see the stream well?
You're subtracting it by 0.5. What do you mean, like, how? So the screen is like what? 768 by 1432. So how is subtracting it by 0.5 vec2 make it in the middle? Shouldn't it make it like 1.5 a pixel up or something?
That would, except the UV it's normalizing the whole thing. It's the coordinate divided by the resolution. Apparently zooming in kind of goofs the selection box. But yeah, so when it normalizes it, it basically turns this to 0 and this to 1 instead of this to 0 and this to 800.
Oh, okay.
Yeah, and it makes it a lot more convenient. That way it works for all resolutions, including full screen. I'm not sure if full screen displays right on the stream. Does it?
Yeah, it's displaying.
Okay, good. So then we could have something like a conditional. If we compute this distance here, let's create a new variable called distance. So it'll be a float distance. Oh, distance is a function. Call it dist. Dist equals, and then this thing here, copy that. And so we get the distance from that center point, and then we can have an if statement. So if distance is less than or equal to 0.5, then we have curly braces for the inside of it, and then we can set color to vec3 1. And so if we do that, then we get a big ellipse right there. If we set that to 0.25, then it's a little more manageable. So that's interesting. Although technically that's kind of redundant because we can just copy this to where the distance thing is and remove the definition, and it works exactly the same.
So let me just confirm. So you're basically checking if the pixel is within a region, and if it is, you're setting its color to something.
Yes.
All right.
And there's all kinds of crazy stuff we can do with this. So, have you seen the kind of stuff I've made with Shadertoy? Like what's possible?
I mean, shaders could do anything, but I haven't seen any specific examples necessarily, no.
Yeah, I don't suppose I really need to show the specific examples. We'll just build our way up to that point. Now, one thing you may notice is that it's an ellipse and not a circle, and that is an artifact of the screen being, a rectangle, not a square. Because just like the UV it goes from 0, 0 to 1, 1 up in this corner. But if we want the proportions to be the same, then we would have to divide both the X and the Y by the same parameter. Why is the selection freaking out? That was weird. So if we divide both of them by XX, then we get a circle. It's just offset weird. If we divide it both by YY, yep, it looks a little bit different. And so the offset is, it kind of changes, so you have to adjust where the offset actually goes. So so you want 0.5 for that axis, but the other one, let's see, you'd need like the aspect ratio of it. So it'd be I resolution dot X divided by I resolution dot Y. Suppose that. Oh, that looks weird. I suppose it's the other way. Okay, that's more like it. Okay. And then you could multiply that by 0.5. Voila, back to the center.
What did you just do?
Okay, so it's the same vector offset with the 0.5, 0.5.
Why XX? What's the point of XX? Is it like X squared?
No, that is taking... okay, so this here... Let's get another section down here. So this here is identical to vec2 I resolution dot X I resolution dot X. This and this mean the same thing.
Oh, so you're getting as a square instead of a rectangle.
Yeah, pretty much. And I'm dividing both the X coordinate and the Y coordinate by the X resolution. That way it doesn't get squished. And then when I modify the offset, I need to multiply it by the Y resolution and divide it by the X resolution. Basically taking the aspect ratio. That way it gets, scaled properly and the circle's in the center.
Just explain the second line a bit more slowly.
This one?
Yeah.
Okay. So, on line 4, it has to divide both coordinates by the same number in order to keep the aspect ratio of within the image as 1, so that we get a circle, not an oval. Now, because of this, if we remove this, then it's offset incorrectly. Because if this is 0 and this is 1, this right here is a little bit more than 0.5, and so the half point becomes somewhere up here, and then where 1 actually is somewhere above the screen. But if we add that back in by multiplying it by the y and dividing by the x of the resolution, we kind of squish it back to where it's supposed to go because we're modifying the offset.
So why are you multiplying it by the y?
That way it's shifted correctly up and down.
Okay, so you're doing that for each pixel. Each pixel is being multiplied by the y.
Yeah, but only the y coordinate offset.
Okay.
Because like if we were to change that to 0.25, you know, now it's at the 0.25 section. And, you know, we want the center of the screen to be treated as 0.5. Well, technically speaking, when we get to the Mandelbrot set, we're going to want the center of the screen to be treated as 0. We're going to want it to be exactly the same layout as a Desmos graph, where the x-axis increases going this way and the y-axis increases going this way, and the center is 0. We need the center to be 0. And so, yeah, and offsetting it by 0.5 seems to do that well. So once it gets to these two functions, or these two commands, oh, someone's typing in the chat. Yeah. Okay, so once you get to these two, the UV is already centered around that point, and this is considered 0 for like when it gets the distance. This right here is 0, right in the center. And then this is 1/2, this is -1/2, and then +1/2 and -1/2 on the y are somewhere off the screen. And them being off the screen is as a result of this scaling here. Without that scale, then -0.5 becomes here. Oh, and if that was y. Without that scaling thing, then it becomes, this is -1/2, this is +1/2, this is -1/2, and this is +1/2. But obviously, you know, squishing the grid into a circle like that, or into a rectangle like that, is like doing this on Desmos. So if we got, you know, x squared plus y squared equals 1, then obviously it's going to be an oval if we, you know, morph the y-axis like this. Do you see what I mean?
Yeah.
Yeah, so that's why we do xx and then multiply that by these to rescale it so that that's the center. So now, okay, so just to make sure you got all that right, so did you make something kind of like this on your shader?
Yeah, basically the same thing.
Okay, so now I think we can get into the Mandelbrot set. To prepare for that, the Mandelbrot set occupies a certain radius. It occupies a circle of radius 2. Let me turn that back into a square. So the Mandelbrot set occupies a circle of radius 2. And so what we want to do, instead of the edges being 0.5, we want the edges to be 2. So since it's 0.5 right now, what we can do is take whatever we have right now for the UV, we can take it and then divide it by 4. We divide it by 4. Oh, wrong way. Multiply it by 4. Dang. Yep, there we go. So now it is the correct scale. So this right here is -2. This here is +2. And the -2 and +2 for the y-axis are somewhere off the screen. And
Okay, but by 4.
yeah.
Oh, right. 0.4. 0.5 into 4 equals 2.
Yes. Yeah, and so technically we could compress this into a single line, I think. Yeah. Let's see. So if we were to multiply the 4 in right here, remove that, and then change these for 2, it should have the same exact result, yes. Yes, so we do the UV, equals 4 times that, so it goes from 0 to 4, and then we kind of squish it a little bit, or we offset it so that the center is 0, 0 once it gets to the actual, meat of the program. Now, with the Mandelbrot set, we're not going to be making the color off of, what we, a simple formula like this. It's going to be a bit more complex than that. So, in order to understand the Mandelbrot set, we first need to understand complex numbers and imaginary numbers. And where that begins is with the square root of -1. Have you ever played around with the square root of -1?
Yeah, it doesn't work.
Yeah, normally it doesn't work, but if, because, if we plot out x squared, or greater yet, the square root of x, clearly you can see that it just drops off and stops. But if we have, minus x, square root of x and x squared, these two are mirror copies of each other about this line. So that's what happens when you invert a function like that. And so the problem is that no value of x squared reaches down here into the negatives. And that's why there's no square root of a negative number. But what mathematicians a long time ago brilliantly did was they defined I as square root of -1. And they started to explore what could be done with it. So this necessarily means that x squared equals -1, obviously. And when you have some number and you add it to I, there's no real thing that you can do with this to compress it further. So this is as compressed as it can be. And this is what they call a complex number, is when you have a real number here added to an imaginary number here. And the imaginary number can be multiplied by any coefficient, just like the real number can. And so we can actually plot this out as a point. So this here could represent 4 plus 2i. So you can even name these axes, real and imaginary.
So I is a variable.
I isn't a variable, it is a constant that equals the square root of -1. It basically designates that this number here is on this axis here. And so, in a way, numbers are actually two-dimensional. All the numbers that we deal with are normally on this line. The imaginary numbers, and thus the complex numbers, extend into the rest of the plane.
Okay,
And,
I think I understood a tiny bit of that. So numbers are all plotted out on the y-axis, and if we add square root of -1 to them, they can extend into the x-axis.
Yes, but it's the other way around. The x-axis is the real stuff, and then the y-axis is the imaginary stuff. Now, why is this useful? So, we can actually do the basic operations on this. So, if you're treating this like a vector, if we have another one, let's say, I don't know, 1 minus 2 right here, we can add these two together. Let's actually make that -3. So we can add these two together by adding each of the components together, just like we would a vector. So 4 plus 2i plus 1 minus 3i. Simplify that down. We get 5 plus, minus 1i. And so 5 minus 1, this vector plus this vector equals this vector.
Okay, but why is I useful here?
So I basically designates that it's being used in the other axis. Where
Okay.
Where it becomes really useful is when you multiply two of these things together. Let's actually set up variables here for our points so that we don't get everything all mixed up. So you have A, we'll get B as well. We'll color B blue. We'll close out all these things. Okay, so the sum is just A plus B. We'll make that purple, call this sum. And we'll label these A and B. And so, the sum behaves, pretty, as you'd expect. Change that to be A dot X plus B dot X, and then A dot Y plus B dot Y. So then for the product. So the product of them, so we have A dot X plus A dot Y times I times B dot X plus B dot Y times I. And you're familiar with how you'd expand this out, right?
Yeah, distribution.
Yeah. So then we copy that into these things and copy this into these and just kind of repeat that until everything's all simplified down. Move that I to the end. Okay, so now we have this. So, first thing to note is that there's two i's on this number. I squared. I squared simplifies down to -1. So we can remove that and set that to a negative. And just like that, we have a real part here, and we have an imaginary part here. Both these terms have I, so we can pull the I out of there. And voila, we have another complex number.
Okay, that just is, okay, I need you to start from why you set it from A plus B to A dot X plus B dot X.
Okay. So let me write out all the steps that went into that.
No, like, why did you, A plus B, why did you change that to A dot X plus B dot X plus...
When it was all multiplied when it was all multiplied together. Because, like, when you expand this out, you multiply this by this, and you multiply this by this. So you copy that into this. That step makes sense, right?
Yeah, no. My question was, if you had A plus B before, why did you change that to A dot X, B dot X, just for, like...
Oh, this?
convenience? Yeah.
Oh, that's just to show the formula, what it's doing underneath it. Technically, so Decimos adds points, and so it does literally the same thing, but I think showing this form is more productive since it's revealing what it's actually doing.
Okay, and why did I... So when you had I square, you converted I into -1.
Yep.
Because square root of -1 you took, right? So
Yep.
I squared equals -1.
Yes, by definition.
Alright.
Yeah, so whenever you see I squared, it necessarily means that it just converts down to -1. So whenever you have a power of I, you can always reduce it down to a complex number, no matter how ridiculous it is. So we're not going to add extra dimensions. It always boils back down. There's a gnat flying around from my monitor. Okay, we can simplify this down just as we had before, multiplying these things in. And so we end up with exactly what we had before. We have this expanded form, and then that boils down to this. So if we then draw that out as a point, copy that into the X part, and copy that into the Y part, we get a point. And we can color this black and call it product. Now this is where it gets really interesting. So if I start to move around these points, you can see that it moves around in a much different way, right?
Yeah, it's like a infinity symbol.
That's just because of the way I was moving around the A. Now, if we were to lock the components of A and B to the real number line and force them to only move on the real number line, you may notice that the product is always going to be on the real number line. So if we have, say, 2 times 3, the sum's going to be 5 and the product's going to be 6. So this
2 times 3 is not 5.
2 plus 3 is 5. That's where the sum is.
Oh, okay, and the product's at 6, right?
Yeah, and the product is at 6. Then, 2 and 4, the sum is 6 and the product is 8. And so this, the normal sum and multiplication that we have is a subset of this, of all the complex stuff.
Okay.
Yeah, so let's bring this back into the complex dimension. Now, if A is 1, or a rough, 1, then obviously wherever B goes, and the product is going to follow it. Now, if we were to move A around the unit circle, this is where things get really interesting. Let's draw out the unit circle here so we have a reference. Let's bring B closer. See right here? If we move around the unit circle, you may notice that the product goes around in a circle as well. And the radius of that circle is whatever distance B happens to be. And so by having A on the unit circle, we are making the product rotate around the origin like that. See how that
Just
works?
give me like 2 minutes. I actually need to get a notebook out for this.
Okay.
Right, all right. I'm just gonna note down everything we just discussed, so I'll need another minute. So
Okay.
Weird how? It's weird. What? Weird how? It's just weird. I saying weird. It's like, oh, well, it's like weird. Oh, it's just weird. Like weird as a part of this thing. I don't know. Let's take a break.
Okay. Right.
Okay. So, the general takeaway with there's a certain way you can look at this that makes it make a whole lot more sense. So, say we have both of them on 1 plus 1i. The product will be at 2. And so, what we're doing here, you take the angle of A, whatever this angle is, you add it to whatever the angle of B is, and that becomes the angle of the product. Because obviously if one is on the real number line, then the product will be in a straight line directly from the origin to B to the product. Because this one's angle is 0. If this one's angle is 90, then it will be at a 90 degree offset from wherever B is. And the same thing with the other direction. So you add the angles together. The other component is the magnitude, how far away it is. So you take the magnitude of A and you multiply it by the magnitude of B, and that becomes the magnitude of the product. So you're adding the angles and you're multiplying the magnitudes. Does that make sense?
What's a magnitude?
The magnitude is just the distance of the vector from the center.
Give me a second to note that down. Magnitudes are the
distance of the vector, the point, from the origin, the center.
Yeah, okay. I think I understand what you mean.
Okay. Now, if we put A on one of the Pythagorean triples, 3, 4, and then the distance becomes 5, then if we put that at 2, the angles, this angle plus this angle equals this angle, and then the magnitudes, that's 2, and that magnitude is 5, so then this magnitude is 10. Look at that, it's at 8 and 6, so yeah, that magnitude is indeed 10. And there's patterns like this all over the place because of this simple relationship.
Right.
Okay, so were you following for all that?
So basically, when you multiply A by B, well, if you add A and B, it takes X, which is a real number.
Yeah.
It adds those X's together, it takes its Y, and then it adds those Y together. And yeah, that's basically it, right?
Yeah, that's for the sum.
And then the product is when you multiply A and B.
Mm-hmm.
So you're just multiplying all that, and then you get I squared, and then I squared becomes negative, and all those shenanigans. And yeah.
Yeah, and it's amazing the kind of properties this has. Because, if you want to, rotate a point, you don't even need trigonometry if you know where the complex number is. And then you can treat these like complex numbers to rotate the point in the same way. Because, how much simpler is this compared to, cosine of x times, sine of, 4x and, whatever.
I mean,
you just do this.
it would be simpler to think of in terms of trigonometry, but I can understand this as well.
Yeah, it really depends on the use. Different uses have different needs. Okay, so now we get into the next part. What on earth is this thing? So, we begin with a simple little action. An action in Desmos is like this, where you do a hyphen and then the is greater than sign in succession to get this arrow. So if we do z equals z plus 1 and define z as something, and we click that and we basically modify z to be something. And we can change this to whatever we want. We can do whatever we want with it. So, if we set z to a point, let's say we set it to 0, 0. Now this here, the action is z squared plus c, where c is some constant. Let's turn off a and b here while we're doing this. So c will be some constant. Remove these labels. They're cluttering the screen. So we have some constant c. Call that c. Call that z. Move z back to the center. And then c is just some arbitrary number. And we'll also set up an event to put z back to the origin, so that if we move it somewhere, we can just reset it. Now the idea here is to take this function and to run it again and again and again and again and again and again and see how it behaves. So clearly we can square this since it's complex numbers. So we can grab this thing here and replace a and b with z. Now, there's some simplification that can happen here, like zx times zx is just zx squared, and zy times zy is just zy squared. And then you got zx times zy plus zy times zx, which is just 2 times zx times zy. And so this becomes z squared. And so it kind of follows the same rules as before. So then this gets fed into this, and you add c to it. So now, if we run this, it goes to that point, and then it goes somewhere else. And then you just keep on running it, and oh, it has exploded to really, really big numbers.
Why?
Let's see if we move it to right here. And then we run it again and again, and oh look, it has stopped somewhere. But why? If we move it to, say, right here, reset it, and then run it again, oh well, now it goes between 2 points. So what's up here? And like each point behaves a little bit differently. Like right here, this also approaches somewhere, but a little more slowly. Right here, I believe, will get really big really fast. And the pattern for what is causing this is this. So if I open up a where is it? The previews would load. Here we go. My internet's not doing too well today. Okay, so this graph here, this plots out all of the iterations that the little z point goes through when we spam this. And so in this big blue region, it is nice and stable, and it goes through a lot of really cool patterns. You know, as you move it around, like right here, it's like a 3-sided thing, then get like a 5-sided thing. And inside the point, you get like a little pentagram. In here, we get that back and forth between 2 that we got. And in here, it always approaches some point. It's like a weird spiral over here. But then once we... Go on.
That's the, what you call it? Yeah. You know, that little spiral thing that happens in nature, isn't that it?
Oh, you mean the Fibonacci spiral?
Yeah, isn't it the Fibonacci thing?
No, this is not quite related, but there's probably some deep connection in there somewhere that we haven't discovered yet. And like each of these little tiny bulbs here has like a different shape for it and whatnot. And here's the thing, as soon as you leave the blue, it gets all crazy and chaotic. And you know, like some places are more chaotic than others. Like if I get really, really close, it kind of collects itself, and then boom, back to normal. Crazy, normal, crazy, normal. You know, it's funny. There's a tiny little blue speck up here. So if it's crazy, 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 and then up here, normal. Crazy, normal. And isn't that just fascinating how that happens?
Yes and no.
The thing about this shape is that there's infinite detail. Like if you search Mandelbrot zoom, then there are so many videos that just go on for hours and hours and hours. Like look at this, it just zooms in, it just keeps on zooming because there's infinite detail inside this thing. And look at all these spirals and everything. And we can draw this in Shadertoy. And that's what we're going to be doing.
How do they get the different color on it? Is it just...
Yeah, so the different colors. How that is done is... so if it's stable, you color it... You usually color just some flat color. But if it's unstable, you see how unstable is it? How many iterations does it take to escape? Because like right here, it takes, what, 1, 2, 3, 4, 5, you know, and so on to get out. But if you get like really close, it takes a lot longer to get out. And as you get extremely close, it takes much, much longer to get out. In fact, there's not even enough iterations displayed. Well, something weird's going on with the graph here. Yeah, some of the points are so way out there. But yeah, so you basically measure how fast, you know, does it go crazy. And that's how you color it, basically. So, you got that, right?
Yeah.
Okay, so now we can start, you know, drawing this thing. So the first thing we need to do is see how many iterations does it take for it to go nuts. Obviously, you want to put a cap on it, since while it's stable, it will continue to infinity, and we don't want to crash Shadertoy by doing infinite iterations. So we can stop at, say, 1,000. So if we define, let's have a section here, initialize variables. So if we have an int here, we can call it iteration limit. We can set it to, say, 1,000. And we can remove those. Don't need that anymore. And so then...
So shouldn't it be called recursion limit?
Oh, we could have called it recursion limit. We can call it whatever we want. Okay. So now we need to set z. Z is a vec2, and it starts off as 0, 0. Oh, this needs to be defined as a vec2 type. Whenever you initialize a variable, you have to specify what type it is. Now, C is based on the pixel, since this here is C. And so, basically, we just set that to UV, right? Yeah, because this is 0, 0 for UV and you know, so on. So we could really just do vec2 equals C equals UV. And that should work just fine, because we've already set that up before. And now we can actually do the thing. So if we have a for loop here, sometimes I forget the format of a for loop in GLSL.
Okay, int I equals that. Int I equals 0 semicolon int.
Yeah.
I is less than I plus plus.
Yeah, and then I is less than recursion limit. Yeah, that should be it. Actually, we need to initialize I outside of it, I think, because we need to access I afterwards, because we're going to suddenly break the loop. So if we do int I equals 0, and then just kind of... Actually, we don't even have to... Yeah, till we initialize it. And we initialize I is 0, see when it's less than the recursion limit, and then I++ for adding it, and blah, blah, blah. Okay, run iterations for the comment there. So then, basically what we do is just run this function here. So if we were to actually just copy that into here, remove all the decimals formatting, and adjust it so that it's in the proper format and everything. So instead of squared, we do times z.x, and right here as well times z.y. Put some spaces between the pluses and minuses so it looks nice.
Have like power thing?
It does, but using the exponent is a lot slower than just doing this, because it references natural logarithms and stuff, and all that just to multiply something by itself is way unnecessary.
Okay.
Yeah, and then we add c, and we set z to this. And then we have to see if this point has escaped the center. And so there's a special function for that. Length returns the length of a vector like that. So if the length is greater than 2, if it escapes the radius of 2, because if you notice here, the entire Mandelbrot set is contained in the circle of radius 2, the entire thing. Like way out here at this little point is like the very tip of it. But if you take a step to the left that's infinitesimal, you're outside. And that's the nature of the chaos. One tiny infinitesimal step can completely change the outcome. So if the length is greater than 2, then we break the loop. Else, actually no need for else, we just repeat the cycle. And so this continues until it hits that point, basically. And now we need to decide what the color is. Assign color. So first things first then. Actually, we can set it to is less than or equal to the recursion limit. That way it stops at the recursion limit. If I is equal to the recursion limit, then we can set color. I need to initialize color. Vec for color. Let's call it full color, not just col. Okay, so color equals vec for 0, 0, 0, 1. Else, if actually not even if, just else, then right here we would color it based on what the iteration actually is. And let's suppose with the iterations, like 1,000 iterations is like the brightest, and then 0 iterations is the darkest, until it finally gets to the set where it's absolute black. So it's like gets brighter and brighter and then dark. So for now, we can have color equals vec for, have 1 as the alpha channel there, and then for the RGB, you want this to be grayscale. Do the same thing here. That way we have the color written here. Actually, wait, what are we doing? That has, can't assign this as a vec 4. Silly me. Color is supposed to be a vec 3. Okay, that's better. So then for this,
Isn't it, vec 4 because you want alpha as well, just in case?
we don't need the alpha, is the thing.
Yeah.
Yeah, and so we do I divided by the recursion limit. However, these need to be floats while we do the division. So convert these two into floats so we get the proper value. Yeah, float I and float that. Yeah. And then, yeah, that should be it, right? I guess we'll see.
Nope.
Oh, something weird happened. So, now we gotta figure out what on earth this mess is. So, let's see where it went wrong. Let's see here. I can actually reference another Mandelbrot shader that I had made. If it would load. Okay, so let's see what I did here. Oh yeah, pretty much just the same thing then. Okay, back to this. So, yeah, UV is assigned as it should be. Z is initialized as the center. And C is the UV. Okay, so...
I have the same thing as yours, but mine isn't even just white, it's just black.
Odd.
With a tiny white border.
Okay, so then... yeah, that math is right for that purpose. Oh. We didn't turn that into a vec2. Ah, that's much more like it. Okay. Okay. Here, let's see what yours looks like. Okay, so yeah, that is the proper shape for it. Oh, looks like with mine, yeah, yours actually has the proper outline. For some reason on mine, the inside of mine was colored white. If I equals recursion. Did I do the equality incorrectly? I don't think I did. If it's recursion limit. How about if it's greater or equal to recursion limit? Ah, there it goes. So it must go one more than recursion limit then. It's kind of a weird artifact of the for loop. Okay, so now we have our Mandelbrot set. However, the outline is really rough. So what we could do is, instead of using a linear thing, we could use, I'm thinking, the natural log of x, perhaps, where it kind of like approaches a value, maybe a different function. But either way,
Reduce the recursion limit, it does get a bit smoother.
yeah, exactly. So we want it to approach white sooner instead of just being linear, and any number of functions can work for this. It's completely up to our preference what we do with it. Oh yeah, that's what happens when you change the recursion limit. Actually, hold on. If you set the recursion limit not to 1,000, but to something based on time. So if we do I time, and then let's say every second, it adds another iteration. So if we do that, oh, something weird happened. Oh.
You haven't declared that.
Yeah, recursion limit. I misspelled it. Okay, so restart it. Isn't that freaky looking? So this is it adding one iteration at a time. Let's make that a little bit faster. You could do times, I don't know, times 3. Yeah, and so this is it adding one iteration, or 3 iterations every second, and so you can slowly see it getting more and more fine. And the idea is, what does this look like as it approaches infinity? Yeah, and I love all the lightning patterns on the edges and stuff.
Could you go back to the code? I feel like I screwed something.
Okay.
I didn't do the intro.
Yeah. Okay, now to fix that darkness problem, I would like it to be brighter. I really think the natural log would work for that, but the problem with the natural log is that it doesn't have an upper bound. Maybe the squishification function. There's a certain function I like to use. I believe it's x divided by the absolute value of x plus 1. No, that's not it. Absolute value of x plus 1. Yeah, there we go. Okay, so x divided by the absolute value of x plus 1. I really like to use this function because it always approaches 1 as the number gets larger and larger. And so we can actually feed the iterations through this, disregarding the recursion limit. And so
I would just like to state something for the YouTube video. It's a bit different for everyone. You'll have to. I'm not, because it's based on resolution, right? So for me, I have to divide time by 30.
yeah, it's based on what the FPS. No, it's not based on FPS. How do you mean divide time by 30?
I sent a screenshot.
Oh, you see, you probably didn't hit the restart button. This little thing here to restart it.
Oh.
Yeah. Okay, then absolute value of.
Oh yeah, now that makes it a lot better.
Yeah.
But it's still a bit weird.
Some freakies going on here. Oh, the brightness isn't inverted or anything. Okay, so now I think it gets bright a little too fast. So what we can do with this function is divide both or just one? No, it's both. You divide both by the same thing. It still approaches 1, just at a different rate. If we set n equals, I don't know, 0.1, then multiply both of these by n, then we can set n to change the rate at which it does this. We can set it to like some smaller value. So we multiply that by, we'll have some value here. It'll just be a constant. 0.1, then multiply this by 0.1 as well. Boom. Ah, that looks nice. We make that like, say, 10. Ah, isn't that sweet? And we can even give this like a hue. Like what if we wanted to give this a golden hue? What's a good color for gold? RGB value. Let's see, minecraft.fandom.com/formatting codes. I always like to use this to see what the RGB values are for the colors.
Let's use FAA.
Yeah, this right here. So we gotta convert that into the proper format. So it'd be 170 divided by 256. So okay, so 2/3 is for that one. So it's 1, 0. Infinite sixes, and then 0. So go back to this, and so the color is then. Well, this would really become the shade, wouldn't it? Yeah, so this becomes the shade then. So we do float shade, and then shade is equal to all this stuff in here, and then it multiplies our gold color by shade. Boom, now we have a golden Mandelbrot. So, what have you learned today?
Making fractals and complex numbers.
Yeah, isn't it epic?
Yeah, I think a decent grasp of Shadertoy now.
Yeah, and this shader here, I colored it a bit differently. I actually made a traversable camera so you can actually zoom in on it. And it's funny because if you zoom in enough, it's weird because there's tiny Mandelbrots buried inside of it. But if you zoom in enough, you'll hit the floating point precision limit where it just gets all pixelated like this. If it were to use double precision, then we could zoom in a lot more. But unfortunately, it's not. This one actually uses 10,000 iterations. And I have another shader very similar to this with the traversable Julia set.
Can you go back to the first set that we were working on?
Yes. Let me go to the traversable Julia set real quick. Okay.
Right. Just informing. I seem to have screwed something up. Right, wait, I screwed something even more up.
Uh-oh.
There we go, got it.
Okay, what's your Mandelbrot look like?
Basically the same as yours.
Okay. And so what the Julia set does, it's quite similar to the Mandelbrot set, except instead of C being every pixel, Z becomes every pixel, and C is the constant. So you're like switching the roles around. The base version is a circle, but if I click and move the mouse around, you get all these weird fractal shapes. And this is by moving around where the Z point starts off at, I believe it is. Let's see. Trying to remember exactly where that. Yeah, because the pseudo memory system here is a bit complex. That's how I can get the actual movements of the camera, and I'll discuss pseudo memory and Shadertoy at a later date. But yeah, the gist of this is basically when you switch around the roles of C and Z, and you get this whole family of fractals. And what's fascinating is, so long as the point is inside the Mandelbrot set, you get one complete shape. But as soon as it goes outside the Mandelbrot set, you get the chaos, the disconnected chaos. Inside the set, outside the set. And so it's fascinating how they're so deeply connected with each other.
This is fun. I need to go eat food now. I will see you later. Is class over here?
Yes, that concludes today's lesson.
Alright, see you.
Okay, I will see you later. And that concludes today's lesson. Next week, we will be discussing 3D projection in Desmos. So stay tuned for that one.